Okay, so hi, my name is Paris, and I'm a PhD student at the University of Cambridge. My supervisor is Pietro Leo. So today, the title of my talk is Perspectives on Algorithmic Information Theory and Evolution. So really what I want to talk about is evolutionary algorithms in the context of sort of optimization and learning, and some of the problems with these algorithms that have existed for a long time and people haven't really been able to come up with solutions for, including a lack of theory. And then I'm going to talk about a specific result within AIT due to Gregory Chaitin that is kind of a promising first step, and some of maybe the issues with it and some of the kind of benefits of it. But to kind of start off with, just a little bit about evolutionary computation as a field. So it takes essentially the kind of basics of evolution, right? So we have hereditary multiplication, so generations, in some sense resemble each other. There's variation through mutation, recombination somehow. Then you have some form of natural selection, right? And these can be implemented in lots of different ways, but essentially these are the three basics. And as I said, these algorithms get applied to optimization problems, machine learning problems, and even people just essentially trying to create what we call artificial life. And so, quick history of the field. Actually, you could argue that the sort of beginnings of it began with Alan Turing, who sort of suggested in the late 1940s a sort of genetic search. And then I had Bremerman, who did actual computational experiments using genetic search. But the field didn't really kind of blossom until the late 60s, early 70s. Because guys like Vogel, Holland, Beckenberg, and they came up with sort of somewhat independent subfields of evolution computation, like genetic algorithms and evolution strategies. And there's subtle differences between all of these and also in genetic programming, which Koza kind of popularized in the 1990s. But they're all essentially sort of the same kind of idea, right? We have a bit of variation and subsequent kind of processing through these generations and natural selection. So, okay, so also really quick, this field has done well. It's historically, it's had a lot of success, creating patentable ideas in engineering and operations research. And so even more recently, people use it in neuroevolution and training neural networks, which it's nice because it's a very parallel sort of training method. So it scales well in high performance computing. And even as recently as a few years ago, people have found it can quite reliably discover basic machine learning algorithms. So, all right, despite these successes, I'd argue that kind of this field had a bit of its heyday in the 90s when probably most of the work was done, and has kind of quieted down a little bit, especially in the last 10 years with deep neural networks. But why is that? And there's clearly like a big disconnect between evolutionary algorithms and what you see in the natural world, right? But we clearly haven't created something to the level of sophistication as like a human, right? So why is this the case? Why is it sort of failed in this respect? So probably the kind of predominant idea is that we just don't have enough computing resources. So if you think between yourselves and maybe the first life on Earth, there's probably been on the order of trillions of generations between you, and that's just the depth, but there's been an incredible amount of breadth as well. And so you can do kind of back of the envelope calculations, and you figure out that if the amount of evolutions has been something order of magnitude far and beyond the biggest supercomputers we'd have today. So potentially we just don't have enough computing resources. However, there's sort of a lot of things that these algorithms are missing, a lot of low-hanging fruit, and in some ways they're a bit naive, right? So there's a lot of ideas in evolution that we've kind of developed over the last 150, 160 plus years since Darwin. And so you've got ideas like open-endedness of the kind of problem, major transitions in organizational structure. So I think, for example, the jump from asexual to sexual reproduction, single cellular, multicellular organisms, these kind of things, even in some ways, the development of language. And so genetic drift, multi-objectivity, all these things, there are algorithms, evolutionary algorithms that hard code these in, right? So I can say, well, maybe I can imitate sexual reproduction by forming some kind of recombination algorithm, right? But there's very little that have these as emergent properties. So there's that, which I would argue is probably the more important thing to address first before jumping to the conclusion that we just don't have enough computation power. There's also a real sort of lack of good theory in the field. There are things like schemata theorems and even kind of more simple approaches, just using like basically Markov chains that do convey some insight, but it's very hard to predict what these algorithms are going to do. Okay, so why algorithmic information theory then? Well, as I talked about with like these major transitions, in many ways, you might want to think of evolution as a sort of propagation of information, right? So we're collecting some information in our environment, and obviously natural selection is acting, but as I said with the major transitions, it's postulated that essentially one of these transitions was the emergence of language, right? So we're passing on information about our environment, but it's not encoded in our genotype, right? It's encoded in word of mouth and books and writing and all that, right? And so obviously algorithmic information theory is clearly general enough to deal with all the computational and computable really and information theoretic aspects of this. But can we actually get some precise results, right? Can we get something that's a bit useful? So this kind of leads me to this work by Gregory Chaitin, who is usually recognized as one of the three founders sort of algorithmic information theory. And a little over a decade ago, he wrote this paper which he called Metabiology, which makes some progress towards some results. So I'm going to talk about metabiology for a bit now. So what is metabiology? So you start off with your additively optimal, prefix-free universal Turing machine, right? And the organisms are what you would think of as organisms are actually programs for this universal Turing machine, right? And the game kind of works like this. I run the program, I get some output, I measure the fitness of this output, I mutate the program somehow, and I get a new one, run it again, I get some fitness and compare the fitness. And if I have a better fitness, I keep it, right? So it's a huge oversimplification of this whole process, but this is where we're starting simple, right? So, okay. Now, there's two things I haven't said yet is how do we do the mutations and how do we measure the fitness? And this is kind of where the interesting part is. So the mutation in this respect is also a program, right? So you might think, okay, well, say I've got a program, a binary program, zeros and ones, and I want to mutate it. I might flip a few zeros and ones here, right? Little bit flip, and I get a different program, and maybe I'll compare these two, and I'll set some kind of mutation parameter. But instead, Chaitin decides, okay, well, we're going to make these programs, and we're going to randomly sample our programs. So we might sample some mutation program M, feed program A into it, right? Run M with A as input, get B, right? And now you compare A and B, and we go and continue the cycle. But how do we sample these? So we put a nice algorithmic probability prior on it, right? So the probability of mutation, and these are prefix-free mutations, so these probabilities are less than or equal to 1. And this kind of, if doing it in this way, by doing it 2 to the negative length of that program, gives us these nice results in algorithmic information theory where we can say that we have program A and we want to look at the probability of jumping to program B. It's simply just 2 to the negative, approximately 2 to the negative Kolmogorov complexity of B given A up to a constant, right? So that's kind of nice, right? That kind of a good characterization. But the real get of this is that we see for a particular fitness function a collapse in the amount of time it takes to get this n level of fitness from 2 to the n time to between quadratic and cubic time, which is obviously a huge jump. So a few more specifics that sort of are important. We are using oracles just to make sure that everything halts, the mutations and the programs. And the fitness function is very specific. So the fitness function is, so if you've heard the busy beaver function, right, that's, there's many different ways to formulate it, but kind of nice way to do it is say it's the biggest number output by an n-bit program. That's the busy beaver number n, right? And so Chaitin actually says, okay, well, we're going to change this a little bit what we're going to do is we're going to kind of enumerate all the halting programs, and we're going to get improving bounds on the halting probability omega, right? And then we're actually going to redefine the busy beaver number as the least j, so a number of programs for which the first k bits of these lower bounds on the omega are correct. So it's actually kind of a bit easier to just visualize. So say we knew omega. As you added more and more programs to this, you get these improving approximations. And so actually, it's quite easy to show that these two formulations of the busy beaver number are approximately equivalent. So up to like a sort of log. Okay, so I was going to go through, well, actually, I will go through the proof a little bit in more detail. So, right, so the way that we kind of get to this sort of quadratic, sorry, a little bit less, more than quadratic approach is that we consider certain mutations which essentially are going to try and add a bit of information to the outputs of the programs, right? And the thing is that when we're using the oracles, if we add a bit of information and it goes over the omega, then a program which kind of essentially runs all of these ordered halting programs will never halt. So the oracle will tell us, okay, this doesn't halt, so you can't actually do this mutation. But if it does halt, then you can, and you've incremented the output by 1 in the place of k. So so either the program never halts or it increases in fitness. And the kind of nice thing about this is that, right, so if I call these mutations mk, right, so I'm trying it in the kth place. If I did it in order, I would approach busy beaver fitness k in k time. But obviously, we're randomly sampling these, right, with this Solomon prior on it. But you can still prove that because it has this kind of probability, 1 over c k log k, that actually in n squared time, you'll actually, because you're just randomly sampling these, you'll get the order m0, m1, m2 that will eventually appear in this amount of time. And there's also this other feature, this proof that other mutations don't really affect this, because essentially this is just looking at the output of the program, which is always preserved because you never have a sort of decreasing fitness. So there's also, in this paper, there's also some results about hierarchical structures, which are a little bit less developed, so I won't really talk about them here. But okay, so what are some kind of problems with using this as a kind of way to sort of analyzing evolutionary algorithms? Well, obviously there's like the usage of oracles, which can't do in real life, right? And you could argue that this very narrow choice of fitness function kind of only potentially works when you have a sort of directed kind of mutation path where you're always retaining the best fitness. That's okay. That's maybe fair. And actually, like a lot of the interest in this paper, it actually comes from people like Scott Aronson, who are complexity theorists, who is actually just very interested in the busy beaver function, because it says something quite interesting about the busy beaver function, in that busy beaver numbers have a lot of information to say about the next busy beaver number, which is a little bit surprising. However, all right, it's a pretty rigorous first step towards kind of using AIT as a sort of tool to study evolutionary computing. And there are definitely real world analogs to this, in terms of algorithmic mutation. So you might think of something crudely, maybe something like trisomy 21 is clearly an algorithmic mutation, right? But it also is a bit guilty of some of the sins of earlier evolutionary algorithm approaches, where it's not quite all encompassing. It's not obvious that you could have major transitions just by making your mutations algorithmic. However, it is more generalized. So I think it's a good kind of proof of concept, but perhaps more interesting ideas might be to look at thermodynamical theories of evolution, such as those put forward by Jeremy England, and look at those through the lens of AIT. But however, I think it's quite an interesting first step. So I think that's my time. So any questions?
So just continue our topic.